Okay, yesterday we had started with revision, right, of the first chapter, that is solids. So the other day during revision, we had finished the classification of solids, and then we had gone into what is meant by crystal lattice, and then the unit cell, right. Then we had seen the categories of unit cells or types of unit cells, namely two, primitive and centered, right? And in centered we had BCC and FCC and ACC. Then we'll see the 7 crystal systems. So there are 7 crystal systems, starting with the first one, cubic. Okay, after cubic, tetragonal. Then comes third one, ortho, rhombic. Fourth one, hexagonal. Then comes rhombohedral. The sixth one is monoclinic, and the seventh one is a triclinic, right? So what is the difference? The difference is the characteristic feature. One is the edge length, which may or may not be perpendicular, and second one the edge angles. Depending upon those two, you will get these 7 crystal systems, right? Another important thing in this chapter is the calculation of number of atoms in the unit cell. The calculation of number of atoms in the various types of unit cell, that is BCC, FCC. Fine. Now if you take the primitive, first one, the primitive unit cell, right? So what is a primitive unit cell? There are 8 particles occupying the 8 corners. So if you represent this, and here there will be particles present at the 8 corners. So each corner particle contributes 1/8 towards building up of the entire crystal. So since each corner atom contributes 1/8, see, it becomes number of atoms in the primitive unit cell is nothing but 8 particles at the corners, each is contributing 1/8. Therefore 8 into 1/8 is equal to 1 atom. Okay. So we say in a primitive unit cell we have 1 atom. Similarly, if you calculate number of particles present in BCC, you get 2. Isn't it? So if it is second one BCC, the body center Q, there are 8 particles at the corners and 1 particle is present at the body center. Right? Therefore, 8 particles at the corners into 1/8 per corner particle is the contribution. So how much you get? You get 0, 1 and Then what is at the body center? The one which is at the body center is independent, right? So you have to take it as 1. So 1 body center atom. You have to write it as 1 into 1, that is equal to 1. So totally you get 2 atoms. So number of atoms in BCC, if you see, it is 8 at the corners. Each particle at the corner is contributing 1/8. So you get 1 atom, 8 into 1 by 8. 1 is at the body center. Okay. Therefore, you have to take it as independent 1. So 1 plus 1, you get 2 atoms. Then comes the FCC further. This FCC, you know, if you take the FCC, there are 8 particles at the corners and 1 on each face. Okay, so 1 on each face. Therefore, since they are on the face, their contribution will be half per unit cell, because this can come in contact with 1 mole and therefore it can be shared with another unit cell. Therefore, the calculation becomes 8 corner atoms into 1/8 per unit per corner particle. So 8 into 1 by 8 is equal to 1, and there are 6 present at the 6 faces. So 6, and each one is contributing half. Okay, so 6 into half becomes 3. So the total becomes 4 atoms. This is how we do the calculation of number of atoms present in the unit cell. This can be a probable 1 mark or 2 mark question. Calculation of number of atoms in the unit cell. They can ask you BCC or FCC or the simple primitive unit cell. The next important question that is asked in solids chapter is calculation of packing efficiency. This is a very important 3-mark question. So you should know the derivation to calculate the packing efficiency of FCC, then BCC, as well as the simple Q. Therefore, let us see the first one. What is that? Packing efficiency in HCP, or we can call as CCP. So the first thing, it is always a 3 marks question. Therefore, the first thing is 1 mark is allotted for the diagram. So, diagram, we show it now. So, first draw the cube. Okay, that mark of the points A, B, C, D, E, F, G and H. draw the diagonal. It is called the face diagonal. That is AC. Then what you do? Call this as B. Now the edge lengths, you can take them as A. Then take the center and draw a circle. Then take the center and also draw a circle. And in between you draw another circle. Okay, so this is the diagram, and you will get 1 mark for the diagram. Okay, then the derivation. Let the edge length A and the face diagonal equals B. Face diagonal is B. So, in triangle ABC, I need the diagonal. This AC square. It is nothing but, since AC is equal to B, I can write it as B square, which is equal to BC square plus AB square. Since both BC and AB are edges, and you have taken edge lengths as A, I can write this as A square plus A square, that is equal to 2A square. Therefore, B is nothing but root of 2 into A. Okay. Now, this B, the face diagonal, is always equal to radius of 4 spheres. Okay. Or we write B is equal to 4R, where R is the radius of the sphere. Okay. Now this is equal to root 2 into A. Isn't it? So A is what? A is equal to 4R by root 2, which you can write it as 2 root 1. Okay. And if it is R, if you want R is equal to A by 2 root 2. Okay. So R is equal to A by 2 root 2. Okay. Now, the idea was to get the edge so that we can cube that to get the volume, right? Therefore, how many spheres are there in HCP and or CCP? There are 4. Whether it is FCC, HCP or CCP, there will be 4 particles or 4 atoms. So, to get packing efficiency, I need the volume occupied by the 4 spheres in the unit cell. Okay, and I need the volume of the unit cell. Volume of the unit cell I will get by cubing this, and volume of the atoms present will be given by the volume of the sphere formula. Okay, therefore What all I need? I need volume of the 4 spheres in the unit cell. It will be given by 4 into 4 by 3 pi r cube. Okay. Then I need the volume of the unit cell. That is nothing but a cube. So what is my a? A is 2 root 2r the whole. Right. So this divided by this multiplied by 100 will give me my packing efficiency in terms of percentage. Therefore, packing efficiency is equal to volume occupied by the 4 spheres in the unit cell divided by total volume of the unit cell. Multiplied by 100. Okay. So now substitute. What is the volume occupied? 4 into 4 by 3 pi r cube divided by 2 root 2r cube into 100. So this gives you 16 by 3 pi r cube divided by 16 2 root 2 r cube. So 16 root 2 r cube multiplied by 100, that is equal to 74%. Okay. So some of you can directly write it here. Okay. You can directly convert that into percentage, that it is 74%. This is the most common question that is asked. Okay. So if you see the question papers, you will see that this is the most common question. Fine. So packing efficiency comes to 74%. Then comes the packing efficiency of BCC. Body centered cube. Again, the diagram is very, very important. Okay, so this is A, B, C, D, E, F, G and H. Now first draw, call this as B. Then draw a diagonal. This is C. Okay. Now what do you do? Divide this into 3 and draw the 3 circles at the center. Similarly, draw one at the center. The third one. Okay, once you draw this, take this as the center, draw a circle here. Okay. Then take this as the center, draw a circle here. Then take this as the center, draw a circle here. Okay, then take this as the center, draw a circle here. Then take this as the center, draw a circle here. Then take this as the center, draw a circle here. So this becomes your diagonal. So this is the body diagonal. This is C is the body diagonal, whereas B is the face diagonal. So this diagram is very important because diagrams always carry one mark. Okay, now you know the body diagonal is what? C, whereas the face diagonal is equal to A, right? And again the edge lengths are A. So edge length we have taken as A. So first take take this triangle. In triangle EFD, okay, B square is the face diagonal. It is nothing but A square plus A square, that is equal to 2A square, or B is equal to root 2 into A. Okay. Now in triangle AFD, I have to find C. So in triangle AFD, C square is equal to A square plus B square. Okay. So that is equal to A square plus 2A square, that is equal to 3A square. Okay. So C is equal to root 3 into A. Now in BCC, the body diagonal C is equal to 4. And that is equal to root 3 into A. So I can get A. So A is 4R by root 3. So you cube this, you get your volume of the units. Right? So packing efficiency is equal to volume occupied by 2 spheres, because BCC will have 2 spheres or 2 angles, divided by total volume of the unit cell. Multiplied by 100. Therefore, substituting, you will get 2 into 4 by 3 pi r cube divided by 4 by root 3, okay, r the whole cube into 100. So if you want, you can go on simplifying, or I will tell you directly write it as 68%. Others 2 into 4, 8 by 3 pi r cube, this will become 64 divided by 3 root 3 r cube into 100, that will give you 68%. Okay. So this is 1 mark up till that calculation of C, another mark, and substitute it, you will get another mark. So totally 3 marks.